the step gets smaller, it gets closer to the solution?
Up to now, looks like so, right? Should we further refine it? Okay, how many n would you like? Huh? 10,000. Well, I'm not entirely sure, but let's try it anyway. Hey, it did finish. Okay, so now let's try it again. Now it's pretty good, huh? It's not perfect yet, but it's much better than what we had before. Right? I think the n over 2 thing is a little bit. It should be n over 2 plus 1, right? Otherwise, it's not going to be setting the same initial condition, right? But so that explains the shift because this is really x equal to half point. So we should have set from here. But other than this, we actually looks like have a pretty good solution. But n really has to be pretty large. Okay, so now you kind of see the tremendous expense of a first order scheme, right? I mean, as you add more spatial points, 10,000, it's not just adding more spatial points. Look at how many time steps OD45 has to integrate, right? 24,000 time steps. So the number of time steps you have to integrate goes pretty much proportional to how many grid points you have. The more grid points you have, you can imagine why OD45 chooses much smaller time steps, because if you just fix a grid point and think of how the solution is going to evolve, okay, fix a grid point. The solution is going to move in towards the right, so the solution at that grid point doesn't change, right? And then suddenly it has to go from up here to down here. It's a pretty stiff system, right? You need a pretty small delta t to resolve that. All right. Okay, so our first order scheme works, right? But it's not that good. By the way, how about solving this, the same equation for a negative a? Right? What if we set a equal to negative 1? What do I need to change? So if I take the same equation and set a instead of equal to 1 to negative 1, what do I need to change in this code? Just that single line, right? I can just take it to negative 1 or negative pi if I want. All right. Well, let me take it to negative 1 because I want to see the solution at the same place, right? So then let's run it. Okay, it finished. Let's plot it. Ten to the 306. So the scheme actually doesn't work if I have a negative u. Okay, let's see. Let's actually take this in a little bit. So if I approximate the spatial derivative with a backward-looking difference, okay, it works for positive a, which means when the solution is moving or propagating towards the right. Doesn't work when the solution propagates towards the left. right? Yes.
So if it's moving towards the left, does that make it implicit?
It does not make it implicit because remember, what do we mean by implicit? What we mean by implicit is that in order to get the next time step solution, we have to actually solve a system, right? We have to, there are more than one unknown in the equation. So the last step solution appears more than once. In this case, we have an initial condition which specifies the solution at every grid point at once, right? When we advance to the next step, we shouldn't be looking at this. We should be looking at our space-time plot, right? We should be looking at this. So initially, we have all the solution. As we advance in time, we compute the solution at the next time step at once. So it actually doesn't make any difference if we discretize the solution forward or backward in space. Time matters, but space actually is symmetric, right? If I look towards the left, it's no different from looking towards the right. Time is not symmetric because I have an initial condition. I don't have a final solution, right? I want a final solution, but I only have an initial condition. So space is actually not very sensitive to if you discretize towards the left or towards the right. Yeah, good question though. Okay. So what if I want to solve the equation when the wave is moving towards the left? When the solution is propagating towards the left?